Hi, today we're talking about Lewis diagrams. And Lewis diagrams are a way that we use to draw a molecule so that on paper its structure tries to reflect what the molecule actually looks like. Now, you would have learned how to do some of these things in a basic fashion in a previous grade, grade 10 around here, and that would have worked somewhat well for the molecules we use in grade 10. However, we have a problem. So we're going to demonstrate the problem by using sulfur dioxide. In grade 10, and to a certain extent we're going to try it here as well, you would need the valence electrons. So you would count up the valence electrons for oxygen and sulfur. You'd look at the periodic table, both are in group 16, so it means 6 valence electrons. You would draw the atoms with their valence electrons, and you would find out that both have 2 unpaired electrons. You would try to connect them by bonds, so shared electrons, covalent bonds, between the sulfur and the oxygen and the sulfur and the other oxygen. And you would run into a problem because now we have oxygen, each one has an unpaired electron remaining. Now the obvious thing that you might want to do is to connect the electron on oxygen to the electron on the other oxygen. The problem is that's not how sulfur dioxide looks. So your Lewis diagram no longer represents the molecule properly. So what do? We're going to focus on steps that actually work. There's going to be 7 steps in total. You won't necessarily need to do all 7 all the time, but there's going to be 7 steps. At first it feels kind of long, but it will actually start to flow fairly well once we get the hang of it. You're going to initially count all the valence electrons. Now, of course, we know how to do that. Some of the things are going to be ions, which means they'll have a charge. Negative ions will require you to add electrons. Positive ions will require you to lose or to subtract electrons. Then you're going to arrange the electrons around a central atom. Sorry, not arrange the electrons, you're going to arrange the atoms around a central atom. Most of the molecules you'll see from me in this course will have one central atom and everything else is attached to it. Then you're going to connect those outer atoms to the central atom using 2 electrons per bond. And we'll go with all single bonds to start. You will then complete the octets of those outer atoms with pairs of electrons. Pairs of electrons is going to be a key thing for us. Then, now that takes us up to 5. Step 6 is a might have to do it. You might have to add remaining electrons, if you have any left over, to that central atom. And then, take a look at your central atom, you might have to make multiple bonds. Now, the key mistake that most people make at this point, doing these Lewis diagrams, is that they put more multiple bonds than they need to. So always leave that to the end and only do it if you have to. How do you know? We'll do some examples in a couple of minutes. So counting valence electrons, well, that requires us to use the periodic table. The group number is going to tell us a lot about number of valence electrons. Now we're pretty much going to be focusing on the right-hand side of the periodic table. So we're looking at group 13, group 14, 15, 16, 17. Ignore the 1. So group 13, 3 valence electrons. Group 14, 4 valence electrons. Group 16, 6 valence electrons, and so on. So if I gave you a couple of things to try and asked you to just use the periodic table and count up just the valence electrons, what would you do? Write these down, pause the video, we'll come back in a second and take it up. You should have counted up 26 valence electrons for the SO3 2- ion. Don't forget to add 2 electrons for the negative charge. You should have counted up 32 electrons, valence electrons, for the next one, and 28 valence electrons, and finally 32 valence electrons. Don't forget, for the positive charge, to subtract an electron. Simple as that. Okay, how about the central atom? That was job number 2, was to arrange them around the central atom. Central atom is a little bit of a fuzzier thing because there's a lot of different options, but there are some things that help us to pick which one is likely to be the central atom. Sometimes it's the first atom written, unless it's a hydrogen. It will never be hydrogen as the central atom. Sometimes there's only one of that kind of atom, and I'll show you some examples. or actually if you look at the previous ones that you just counted valence electrons for, that actually worked for most of them. And often it's the one that's the least electronegative element. Well, how do we know? Well, we know our pattern in electronegativity is increases to the right and it decreases to the left. So if things are, sorry, decreases down. So things that are more to the left or further down are more likely to be central atoms. So some examples, if I give you some examples and ask you to do the same thing, pick out what you think is likely to be the central atom, pause the video, pause the video, figure out which one you think is a central atom, and we'll take it up in a second. So for the first one, sulfur is a central atom. For the second one, phosphorus is a central atom. There's only one of them. It's not written first, but it can't be hydrogen. Third one is chlorine, and the fourth one is xenon. Now, we don't often see xenon involved in compounds, and this compound might not last very long, but we do have chemical formulas involving xenon, and it will be the central atom. All right, let's actually make some Lewis diagrams. So we're going to start out with sulfur tetrafluoride. Count up all the valence electrons. So sulfur has this many, fluorine has that many. You should end up with 34 valence electrons. All 34 valence electrons have to get on that diagram. And by the way, if you ever end up with an odd number of valence electrons, count it again, because somebody goofed. Either you goofed or I did, and I either gave you the wrong formula or the wrong charge, or you missed something important. Has to be an even number of electrons. Your next job is to arrange them around the central atom. Well, we kind of know how to do that. We're expecting sulfur to be the central atom. So it's going to look something like this. Then we were to connect the outer atoms, the fluorines, with the central atom, sulfur, using bonds, single bonds, where each bond has 2 electrons. So that. Now, if you do a quick count, that takes care of 2, 4, 6, 8 electrons. So out of my total, 8 are already in there. Next job was to complete the octets of those outer atoms. Now, in the case of fluorine, fluorine can get a stable octet, so we do want the true octet of 8 electrons. So we put them all around. And if I do the count there, each fluorine atom has 2, 4, 6 lone pair electrons and 2 electrons in a shared bond, so each fluorine atom has 8 electrons. That gives me 32 electrons in total. How many do I have to keep track of? Right. So I still have to use this next rule. This is step number 6 of add remaining electrons to the central atom. And those are going to go on, well, sulfur, our central atom. Now, if that seems kind of weird because it's breaking the octet rule, that's okay. Some things can break the octet rule. What's more important than the octet rule is all those electrons. If your diagram requires 34 electrons, you better have 34 electrons, octet or not. Now, we don't actually have to worry about the last rule about, if the central atom doesn't have an octet, because it has more than that. Sulfur dioxide. This was the one that established our problem, required us to use something new. So let's try that, see if the system works for it. All valence electrons, we end up with 18. Arrange them around the central atom. And then we're going to put sulfur in the middle again, put oxygens on the outside. We're going to then connect the oxygens to the sulfur. And so far, we're not really doing anything different than what we would have had before, other than the order. Complete the octets of the oxygen atoms. So 8 electrons around each oxygen in total gives us a total now of 16 electrons. Now remember, there was 18 altogether. So we add remaining electrons onto the central atom in pairs. So we have that. Now our original diagram looked a bit different. Our original diagram ended up with 2 single electrons on oxygens. Now though, if I look at that sulfur atom, I have all my electrons, but I don't have the octet. So now I have to go to rule number 7. If the central atom does not have an octet, or I guess I should say at least an octet, now I have to make multiple bonds. Which one do I use? Well, it doesn't really matter. They're both oxygens, they're both the same, but I'm going to move one of my pairs of electrons from an oxygen that's not bonding into bonding with sulfur. Now I want to make something clear. It's not that that's how the molecule would be built. It's not that the electrons go like that and then, oh, let's fill it in. What we're doing is electron bookkeeping, basically, and we're trying to make our diagram reflect the structure. So we end up looking like that. Well, does it matter which one is which? No, it doesn't. Does it matter which one I pick to be the one to donate electrons? If it weren't oxygen-oxygen, then yes, although for our purposes, most of that takes practice and getting used to. When the molecules actually do build, the electrons sort of arrange themselves in whatever works best for them. So we're trying to reflect that, and that's all. I'm going to give you some to try. We'll start with these in class. These will be ones that we try to get our feet wet in with this and get some practice with Lewis diagrams. And then after that, we'll just draw a whole lot more. See you in class.